This is a recording of a talk that I gave at the Los Angeles Astronomical Society Eclipse Banquet. I had lots of technical difficulties during the talk and everyone was really tired, so here's another try at it. Since I figured that most of the people at the LAAS, all of you guys had equipment that you were working with on Eclipse Day, and so you probably spent the afternoon combing through your own pictures. I didn't have a lot of equipment, so I had to spend the afternoon looking on the web for other interesting pictures. This one is a picture from NASA that has the sunspot groups that we saw today, and then it also caught a transit of the ISS across the solar disk. This one is a view from the ISS of the shadow moving across the US. I also like this cartoon. This was also in my feeds a couple days ago. This one talks about how the sun is usually ignored except when there's an eclipse. And now the moon is stepping in front of the sun. But that's sort of the philosophy behind my thinking of giving a talk today on why the sun, and for that matter stars like it, are really not as boring as you might think. This is also just a really good excuse to show some really awesome movies. Most of the movies I show here are in various wavelengths of ultraviolet. There's some X-ray and there's some optical images. They're mostly from spacecraft, from solar observing spacecraft. Yoko was around from 1991 to 2001. It was a Japanese spacecraft. SOHO has been operating since 1995. TRACE operated between 1998 and 2010. Hinode is another Japanese telescope. It's been operating since 2006. Stereo is a pair of spacecraft that have been operating since 2006. And SDO has been operating since 2010. A lot of these missions have an occulting disk. It's basically just a disk that sits in front of the sun. It creates an artificial constant eclipse because some of those missions are specifically designed to see the outer parts of the sun, the corona. Just for reference, I study stars like our sun, but I don't study our sun, so I'll stick bits of my science in where I can. So this is a movie of the sun in ultraviolet from last Saturday and Sunday, so just before the eclipse. You can see the sunspot groups, and you can see all sorts of interesting textures around them, and you can see the corona there too. This movie doesn't have narration, but it does have text on the screen. You can watch the spots moving and changing. Now from the optical, it's going to include some ultraviolet light. And there's a flare. It's back, including some optical. We can zoom in on the spot. So now we have a flare with a coronal mass ejection right there. And then we have a model of that mass ejection reaching Earth. That coronal mass ejection sparked aurora here on Earth. So long, sunspot. So sunspots, which we just saw some of there, are basically like magnetic knots. They look black on the solar surface, the solar photosphere. It doesn't really have a surface like a planet has a surface, but that's sort of what we think of the surface of the sun. And the sunspots appear dark there because they're cooler than the surroundings. You end up with groups of sunspots, and they tend to appear as positive-negative pairs. So like a magnet has a positive and a negative side. You tend to get groups of sunspots like that. And the clumps of sunspots are called active regions. So in one active region, you have several different spots. And this is an excerpt from the movie that we just looked at. So you can see the sunspots moving and changing shape and growing, doing all sorts of interesting things as the sun rotates. The surface of the sun, or what we think of sort of as the surface of the sun, is filled with convection. Convection is basically a boiling pot of water. It's carrying those big cells that move up to the surface of the water. When you look at a boiling pot of water, is carrying energy and mass in convection cells. On the surface of the sun, they're just enormous convection cells, and these cells are carrying matter and energy up to the surface of the sun. But it also turns out it's twisting and turning the magnetic fields. This movie, you can see the surface of the sun sort of boiling. Those big convection cells moving up to the surface of the sun. So flares happen when the magnetic fields in those sunspots release energy, and it turns out they emit light across the entire electromagnetic spectrum, radio to gamma rays, and then those reconnections happen to sort of reorder the magnetic field, and so it reconnects, and the magnetic field is no longer so knotty. It's reconnected in a more orderly fashion. Flares are the biggest explosions that happen in the solar system. They are put in 3 categories. X, which is sort of, hold on to your butts. M is middle, and C is, something happens class. The time scale for flares can be minutes to hours, and of course the sun is 8 light minutes away, so the light takes 8 minutes to get here. But some flares can also launch huge bubbles of material, and that plasma, that ejection of material, is called coronal mass ejections, or CMEs. It takes 3 days for that material to get to Earth from the sun, despite it moving at 1,000,000 miles an hour. So in the movie we just watched, we saw an M1.3 solar flare, and we saw an M2.4 solar flare. That one was connected with a coronal mass ejection, or CME. This movie is taken from SOHO, and there's lots of interesting things to look at here. This is the occulting disk, so it's creating a fake eclipse, and this is the arm holding that occulting disk. You can see lots of stuff coming off of the sun and lots of puffs of matter coming off. You can also see the stars moving past in the background, and near the end of this movie you'll see a planet come in from the left. I think it's Venus, though I'm not sure. But you can see all of these puffs of stuff coming off. All of those are coronal mass ejections, and you can see that some of them are small and fast, some of them are big and slower, but they're almost all extremely, extremely impressive. There's Venus, or whichever planet it is, coming in from the left. So this movie has a coronal mass ejection, but what's happening is the coronal mass ejection is coming towards, well, if not towards Earth, towards the spacecraft that took it. The stereo is offset from the Earth. So the coronal mass ejection generates a whole bunch of particles. And so just like when you have cosmic rays hit your detectors on your cameras, on your telescopes, that happens here too, only it happens in abundance, because the coronal mass ejection is sending quite a lot of particles towards, out from the sun. Now, early on, the stereo is a relatively recent mission, but when some of these missions were new, I went to a talk at the American Astronomical Society in which they were trying to debug something. There was some presentation that I was going to on the sun, and they were trying to debug the projector to try to make sure the movies worked. And so they had a movie much like this that was just looping and looping and looping while they were debugging things. And you really, in your head, I don't know about you, but I hear when that stuff hits, right? And so while this movie at the LAAS was looping and looping and looping, I kept hearing the explosion in my head, and then I realized, wait a minute, it's not in my head, as all the other astronomers around me were quietly making noises, because it just seems like it needs sound effects. Prominences are sort of in between coronal mass ejections and spots. So it's a loop of matter that comes off from a sunspot, but because the magnetic field is so strong, and in a prominence case, those prominences are still anchored to the magnetic field. And so it looks like it might be a CME, but it doesn't end up being one because it stays anchored to the magnetic field. And these things can be enormous. This is just one for scale. You can see that really the Earth is very small compared to this prominence. And we saw some of those around the eclipsed sun today. You could see the prominences. I could, even just with my own eye. I didn't need a telescope or binoculars or anything. This movie follows a sunspot group, and you can see that there's lots of flares and prominences, but it's all tied to the magnetic field. That, it doesn't emit, it doesn't launch anything, it just stays with the magnetic field. So activity cycles. So the sun goes through periods of having many or few spots. And I know that some of you know about this because I've seen in the Yahoo group that at least some of you are looking for sunspots. And we've not had very many lately. But what's interesting is that the sun goes through, when it goes through these periods of having lots or very few spots, at the end of, it does that in about 11 years. And at the end of that, it actually flips polarity, which means that the north pole of the sun, let's say it starts with magnetic north, after 11 years, it flips and becomes the magnetic south pole. No one understands this very well. And no one understands why the sun has been quite so quiet the last few years. It's been really quiet. And the other thing that's really weird is that I learned the other day that the southern hemisphere of the sun is about a year ahead of the northern hemisphere in terms of field complexity. This doesn't make any sense to me, but we'll talk more about that in a second. So here is a mosaic of several different views of the sun, from a quiet sun in 1996, and get a few more spots, 97, 98, 99, 2000. 2001 was solar maximum. Lots and lots of spots. And then it quiets down again, and by 2006 there's not very much left. So this was a prediction from a few days before the eclipse for the corona of the sun this morning. And I don't know about you, but that looks a lot like what I saw with my eyes. And so you can see on the bottom, it's relatively well organized. There's not a lot of structure in the field, but in the corona. But on the northern side, you can see many more knots and texture in that. And that's what that theorist meant when he told me that the southern hemisphere is ahead of the northern hemisphere in terms of calming down from solar max. I have no idea how that would work, how that happens. Magnetic fields are really complicated, and they really govern a lot of the behavior that we see in the sun. The sun is very, very hot, and so it's made out of plasma, which is just charged particles. And because the particles are charged, they can interact with the magnetic field and are often drawn along with the magnetic field. On Earth, the average magnetic field is about half a Gauss, but in the filaments and prominences of the sun, it's between 5 and 30 Gauss, so more than 10 times stronger than what we have here on Earth. And models that include all these magnetic fields are very hard to make, and there's lots we don't understand about the sun that are bound up in the influence of the magnetic field. So the three things I want to talk about, things that we don't understand, is really how solar flares work, the sunspot spike cycle for 11 years, and then coronal heating. So this is a cartoon for solar flares. You can see that they come in north-south magnetic pairs, and the magnetic field lines join them, and you get clumps of them. And here is a picture of the matter being tied to the magnetic fields between two sunspots. So the basics we think we understand, but all the other physics of how that works is really confusing. Here there's a model of a coronal mass ejection, and the lines here are meant to be the field lines, the magnetic field lines, and you can see they sort of bulge, and then eject a whole bunch of matter, and then relax again in a little bit more ordered fashion. So that is somebody's model of how a coronal mass ejection happens, but it's still very confusing exactly how all of this is working. And very recent news, just a couple weeks ago, they had a press release about a flare in 2014 that got squelched. And it just happened to be that there was a suite of telescopes watching that particular region of the sun at once. And they have a long press release, but I really, really liked the words that they chose. The filaments instead pushed up against a complex magnetic structure shaped like two igloos smashed against each other. This invisible boundary, called a hyperbolic flux tube, which is a really wonderful phrase you can drop into conversation, was the result of a collision of two bipolar regions on the sun's surface. But here's the sentence that really got me. This structure eats away at the filament like a log grinder, spraying chips of solar material and preventing eruption. So this is the movie that they released. So unlike the other videos, this one actually has narration, so I'm just going to let it talk.
Did you see that? The sun was caught on camera, ripping apart a structure that was about to erupt. Didn't catch it? Let's watch again. A structure began rising from the surface, gaining energy as it lifted, but then nothing happened. This is the first time anyone has witnessed the teardown of a structure on the sun's surface. Fortunately, at the time of this event, multiple spacecraft were making simultaneous observations in various temperatures. Scientists used those unique views to investigate why the eruption failed. The sun's landscape is controlled by magnetic forces. Within this environment, there are locations where a rapid release of energy is more likely to occur. Known as magnetic topology, distinctive magnetic field lines rule these special areas, and they determine how or whether underlying structures can move outwards. When solar structures with opposite magnetic orientation collide, we expect to see them explosively release energy, yielding a flare and a burst of material called a coronal mass ejection. However, if the magnetic structure dares to move into a less hospitable magnetic region, the surrounding topology will shred the structure, effectively removing magnetic energy and preventing the potential eruption. This observation highlights how the Sun's magnetic topology is a key factor in whether or not an eruption is successful.
So lots of interesting things there. So how magnetic fields are tied up in activity cycles is sort of known but not understood. So because the sun, it turns out it doesn't rotate as a ball, as a solid body. The equator rotates faster than the poles. So the equator takes about 25 days to go around, and stuff near the poles take about 35 days to go around. And what that means is it twists up the magnetic fields. So if you start with a relatively straightforward magnetic field and you wait long enough, the equator is going to pull the magnetic field around faster than the poles. And the longer you wait, the more chance there is for the magnetic fields to knot up. And so what that means is spots first appear at the higher latitudes, but not very high. You don't ever get polar spots. And for the longest time, people thought you could never get polar spots. But then we started seeing them on other stars. So that's a separate talk. But you start with sunspots at higher latitudes, and they move to lower and lower and lower latitudes until they meet at the equator. Then everything reconfigures, and the polarity of the sun shifts. So no one really understands how that happens or why. It's very confusing. There's lots of people who are trying to understand, but we don't really understand that flip yet. The corona is the outer atmosphere of the sun, and that's what we saw when the moon blocked out the sun for us earlier today. This is a picture from 2009. It's just a stunning image. It's a composite where you can see the earth shine on the backside of the moon, and you can see the corona around the moon. I'm sure that these folks are working on making similar images from this eclipse. So the corona is really, really hot, and no one knows why. But you have to remember, when I say hot, then I'm a physicist. And so when I say hot, temperature means the average speed of the particles. So the corona is really not dense at all, but the average speed of the particles is really, really, really high. The visible surface is about 6,000 degrees, but the corona is 1,000,000 degrees. And how you transfer energy from the sun into the corona is not understood very well. Not by Kanye, not by anyone. So the temperature in the corona is so high that means that the matter can no longer be held by the sun's gravity. And so that corona is what's powering something called the solar wind. And you can see streamers moving out from the sun in some of those earlier movies. All of the charged particles and the solar magnetic field makes it out all the way to Earth, but Earth has a magnetic field to protect us. It blocks or redirects most of the influx from the sun. That's why coronal mass ejections make aurora. Our magnetic field channels all of that influx onto the north and south magnetic poles. And when that stuff hits the Earth, then you end up with aurora here on Earth. This is an overly complicated diagram, but was the best one I could find. Here we have the Earth and the Earth's magnetic field here. And here you have an impinging magnetic field from the sun as well as solar wind. And when that solar influence hits the Earth, you can see it create sort of a tadpole shape. You can sort of think of it like a rock in flowing water. It redirects the flow around the Earth, and the stuff that makes it through gets channeled onto the poles. So our magnetic field is really protecting us here on Earth. And that's important because without a magnetic field, we wouldn't be protected from that influx. So other planets like Mars don't have magnetic fields, and they're not very well protected. And there's thought to be lots of implications for that, for life on other planets. There are some people who think you absolutely have to have a planetary magnetic field to help protect the planet so that life can begin. It turns out also that that same tadpole structure where you see in the graphic where the Earth's magnetic field is interacting with the sun's magnetic field, you can have that same sort of structure describe the relationship of the sun's magnetic field to that from the Milky Way, the interstellar magnetic field. And so there is a point at which the solar influence on the local neighborhood is either less than or at least comparable to the influence from other stars. But that's hard to pinpoint. That location is hard to pinpoint. And the best analogy I can think of is that when you're standing in Idaho, the coast seems obvious. You see, the coast is there. But when you're standing on the coast, when you're standing on the beach, where exactly does the continent, does the ground start and the water stops? So here, there's a picture of a beach, but should you put the shore there? And clearly in a previous wave it was there. Where do you put that limit? And that is hard to determine when you're standing on the shore or when you're exploring interplanetary space. Where do you draw the limit? And that's why people sometimes make jokes about how Voyager has left the solar system several times. It's because it's hard to know exactly where the influence of the sun really ends, because we've never been out there before. And that influence, the size of that tadpole, changes with time. When the sun is really active, the tadpole might be very big because the magnetic field is doing all sorts of interesting things and there's lots of solar wind. But as the sun quiets down, that shape shrinks. And so that's why you end up with press releases from multiple people saying Voyager's left the solar system in several different ways, because we don't really know. It's hard to define where that boundary is, just like when you're standing on the beach. Where do you define the end of the land and the start of the water? So now, up until this point, we've been going from the surface of the sun all the way out to the edge of the solar system. But now we can turn around and look more at the sun's internal structure. I showed you a movie of the convective surface of the sun. If you go deep enough, there's no convection anymore. It's just radiative. There's no convection. And then inside the core itself is where the sun is quietly turning hydrogen into helium. Most of a star's life is governed by gravity. Gravity pushes in relentlessly. But when the star is turning hydrogen into helium, for example, in our sun, you have a thermonuclear furnace. And that thermonuclear furnace is pushing back against gravity. Gravity is pushing in, but the thermonuclear energy pushes out, and everything is stable for a long time. The sun has been stable for about 4.5 billion years. We have at least another 7 billion years, but that's an equilibrium that depends on thermonuclear energy, thermonuclear reactions happening in the core. It takes at least 1,000 years. Some people calculate 100,000 to 1,000,000 years to get a photon from the core out to the surface of the sun. Of course, once it reaches the surface, it's only 8 minutes from the sun to Earth. But getting out of the core takes a really long time because you're doing something called a random walk. This is sort of a representation of a random walk, but my mental image of a random walk is sort of like a toddler in a mall, right? I mean, the toddler sort of walks forward and backward and left and right, and, oh, what's this? There's shiny over here. There's noise over there. I'm going to go here. I'm going to go there. You don't know where they're going to go next, and they don't always keep going forward. Sometimes they go backward. And so that's what a random walk of a photon is, too. You can see that sometimes in this cartoon it's going backwards and sometimes it's going forwards. I'm not sure that it has enough backtracking. The way that I've done this calculation has a lot more backtracking because every time the photon hits another nucleus, because the center of the sun is very dense, and so it doesn't have to go very far before it hits something. It's a proton or a neutron, and so it gets re-emitted, but it could be re-emitted in any direction. And so you're equally likely to go backwards as forwards. And so this cartoon seems to have it pretty relentlessly moving forwards, but I'm not so sure it always moves as forwards as this cartoon has. The sun clearly has a magnetic field. We were talking about that earlier. But why? It seems like it's generating its own field, and it seems to be related to convection. Or maybe it's critical to have that region in between the radiative zone and the convection zone. So here you have the radiative zone and the convection zone. Some people think that boundary is important for generating the magnetic field. Or some people think maybe the magnetic field originates deep in the core of the sun. It's really confusing. Other stars much less massive than the sun are thought to be completely convective, and they still have magnetic fields. So maybe that boundary between the radiative and convective zone isn't important. Then there are other stars that are much more massive, and they have convective cores, but not convective outer layers. And they seem not to have magnetic fields, except when they do. Some of them do have magnetic fields in spots. So it's really confusing. We don't really understand this very well, the magnetic field generation. Helioseismology is another really cool thing. It turns out the sun rings like a gong. This was discovered in the mid-1990s. And you can see more than 10 million modes of oscillation on the sun. Basically, you have the whole thing vibrating, and they have periods of several minutes. So I couldn't find any really good movies. Here is a movie of just one mode. It's ringing in just one particular way. And the amplitude is very much exaggerated compared to what is really happening on the sun. Here are static cartoons. So this movie corresponds to this, where you've got like a whole section of it moving in, then moving out, moving in, moving out. Here we have the northern hemisphere, the upper hemisphere here going in, while the part below it is going out. So then that's ringing in a different way. Here's ringing in yet another way. Here's ringing in yet another way. So you have many, many, many modes, even really, really complicated modes. And the amplitudes are not large. They're tiny, but there are many, many of them. And those waves are bouncing around inside the sun. So just like a sonogram, if you know how to read it, it tells us things about the inside of the sun. Some of these waves tend to stay in the convection zone. Some of them bounce through the whole sun, including the core. Some of them are reflecting off that convective radiative boundary. So here's another cartoon. You've got the core, the radiative zone, the convection zone, and then the surface of the sun. So here you have, so they have labeled two different kinds of waves here. P modes are pressure waves, sort of like sound waves. G modes are gravity waves, that are sort of like ripples on a pond. Not gravitational waves, that's something different. That's a totally different talk. So you have, they have cartoon here of these modes moving, these waves, these vibrations moving around inside the sun. These are bouncing off the boundary between the convection zone and the radiative zone. Some of them move up to the surface. So just in the last couple of weeks, some helioseismologists released the news that the solar core is rotating 4 times faster than the surface. So the core rotates in about a week, the surface in about a month. And so that means that not only is there differential rotation or smearing, shearing is the technical word, from the equator to the pole, but there's also difference in rotation rates from the surface to the core. And that difference in rotation rate may be really important for magnetic field generation. And certainly understanding how fast the core is going is important for understanding the star's evolution. So how is this all tying into my research? One of the big themes in my research connects star spots and rotation. So star spots are just sunspots on other stars. Other stars do have spots, sometimes really big spots. The faster they go, the bigger the spots they have. I use data from K2. You may have heard of Kepler. Kepler was a mission specifically looking for planets, and then there were some engineering failures and some clever engineering that allow the spacecraft to continue its mission, but with a slightly different name. It's still looking for planets as K2, but it is looking at a much greater diversity of stars than was originally planned for the original Kepler mission. And so when I use K2 data, I'm not using it to look for planets. I'm using it to look at the stars. And just as an aside, other people do use Kepler and K2 data for studying the ringing of other stars. For the sun, it's helioseismology, but for other stars, it's asteroseismology, not astroseismology, because seismology is Greek, astro is Roman, and so in order to make the word match, it's asteroseismology, not astroseismology. But you can look at how other stars ring too, and look at what the insides of those stars look like, get some insight into what they look like by studying astroseismology. So this is the kind of data I have here. We have brightness as a function of time, and it's about 70 days long. You can see there's flares in there. Here's something called a power spectrum. It's a Fourier transform. If you don't know what that is, it's just math magic. It tells me what period that signal has. And so this is basically one cycle. So in about 0.77 days, there's a big, big spot rotating into and out of view as the star rotates. So think about that. This star is rotating in 0.7 days, not 25 days like our sun, but 0.77 days. Here I've got 2 peaks. Here I've got, again, brightness is a function of time, math magic happens, and then you have 2 periods that come out. There are 2 real peaks here. This one is about 0.35 days. This one's about 0.36 days. There are probably two stars here that each have big spots on them rotating into and out of view. So it's probably a binary. Here, again, brightness is a function of time, and then math magic, and then what it would look like if you could watch it for just one cycle. This is really interesting because this is nowhere near as clean as the ones I was just showing you. What's going on here is probably we're seeing spots moving and changing on the surface of this star, and that's why it's not so clean as it was with the other 2 stars I showed you. There's also some really interesting light curves. Again, brightness is a function of time, math magic. Here you have these really sharp structures. And our best guess as to what is going on is that these are giant coronal loops of plasma being whipped around by the star as it rotates in only 0.6 days. So those stars are all from the Pleiades, so they're 125 million years rather than our sun's 4.5 gigayears. They're rotating very fast. They have enormous spots, enormous prominences, and very strong magnetic fields. So they're going around in fractions of days as opposed to a month for the sun. For the sun at its most active, you get a few percent of the sun covered with spots. Here we have 20 to 40% of the star covered with spots, and they have 10 times as strong magnetic fields because they're rotating so quickly. Some of these stars in the Pleiades are completely convective, so they don't have a radiative core. But understanding when you can get the core rotating faster than the outer envelope, we may be seeing it in some of the data that we have. And it's very, very hard for life to form on planets around a very young star because the star has so many big flares. It likely is going to sterilize the planet unless there's a strong enough planetary magnetic field to protect the planet from those, from that activity, from the stellar activity. Moving on to look at the old sun. Again, this is not my primary research interest, but most of a star's life, like I said earlier, is shaped by the forces of gravity pushing in and the thermonuclear reactions push back against gravity. What happens when there's no pushback? When the sun runs out of fuel? Well, gravity still wins. The core contracts, the outer layers expand, planets get eaten. When our sun dies, it's probably going to eat everything out to Mars. And you can, depending on exactly how, the mass of the star, you may have the outer layers puff off. And this is called a planetary nebula, which has nothing to do at all with planets, but are really pretty. This one is from HST, which is is showing the ring nebula. If you look closely, you can see texture in that outer, in that envelope of gas that's been ejected, and you can see it being blown back by the wind from the stellar remnants. This is another HST image of NGC 6302. This one is very symmetric. This one is really, really not symmetric, but again, you can see texture in those outflows. Another HSD image, this one of IC 4593. Lots of interesting texture. And then this one is one of my favorites. This is the Cat's Eye Nebula. You can sort of see rings here. These are just different puffs, right? So it expands, puffs off a layer, contracts, expands, puffs off a layer, and contracts. And so you end up launching layers of the star in consecutive episodes. So to sum up, the sun is not at all boring. There is a lot of stuff going on in the sun all the time, and magnetic fields are integral to what happens, and we really don't understand a lot of how that happens at all. There are tons of really awesome movies to go watch. Really spectacular movies of coronal mass ejections are my favorite, but there's lots of cool things. And just to put it in context, other stars have spots even bigger than that of the sun with much faster rotation and much stronger magnetic fields. And we can see evidence of star spots and rotation on other stars, which is pretty spectacular. I have one last movie of an M 3.7 flare from 2011 with SDO. So here's this last movie. It starts with a title slide, but you can just watch it. You can see the matter moving around here. Following the field lines. Then there's a flare, and it tries to eject matter, but it doesn't leave. It either splashes down back on the sun or follows back along the field lines. Look at it. Even the stuff out here is getting drawn back along the field lines. It's really spectacular. This person chose a really neat color scheme to watch. You can watch it again. So you see it moving around the field lines here, jumping around. And during the flare, it produces a lot of light, but the matter falls right back down along the field lines, back to the spot. So again, really cool movies out there. Go and find them because you could spend hours just looking at the movies. Thanks.